December 22, 1944. 13:14 hours. Wooded ridge near Bastogne, Belgium. Ernst Hoffmann pressed his body against the frozen earth as the first American barrage began. 23 years of military training had taught him exactly what to do. Flatten yourself. Find the deepest depression in the ground. Wait for the explosions to walk past. Artillery was predictable. Loud. Terrifying, yes, but survivable if you knew the rhythm. Shells hit the ground. You counted the seconds between impacts. You stayed low until the storm passed. He heard his men scrambling into their prepared positions. Textbook defensive doctrine. Spread out. Use the terrain. Let the enemy waste their ammunition on empty forest. Then the sky screamed, not the ground. The air itself. The first shell detonated 30 meters directly above Hoffmann's head. No impact crater. No warning thump of a shell burying itself in snow. Just a devastating airborne explosion that sent thousands of steel fragments shrieking downward in a perfect killing cone. Hoffmann felt something hot tear through his left shoulder. Around him, men who had been invisible in their foxholes began screaming, exposed from above as if God himself could see through their cover. Another shell burst overhead, then 3 more, then a dozen. The barrage didn't march across the landscape like conventional artillery. It hovered, each shell exploding at the precise altitude to maximize carnage. Trenches became graves. Trees offered no protection. Helmets were meaningless against fragments raining vertically downward. Hoffmann tried to crawl toward his radio operator and found the man already dead, killed in a foxhole that should have been perfect cover. 3 meters away, Lieutenant Schaefer was clutching his face, blood streaming between his fingers, making sounds no human should make. The barrage lasted 11 minutes. When silence finally returned, Hoffmann forced himself upright. His shoulder was shredded, but he could move. Around him, the forest had been transformed into an abattoir. Bodies lay in positions that made no tactical sense. Men killed while completely protected from ground-level threats. Of his company's 147 men, 89 would never stand again. Before we continue, click that subscribe button, like this video, and let me know in the comments where you're watching from. It brings me great joy knowing that these war stories and lessons get to people all over the world. Your support helps us bring more thrilling war stories, and trust me, you won't want to miss them. Now, let's get back to the story. The survivors staggered through the snow like sleepwalkers, eyes vacant, mouths moving wordlessly. Hoffmann grabbed a young Gefreiter by the shoulder. The boy's face was gray, his pupils dilated with shock. "What happened?" Hoffmann demanded. "What did you see?" The soldier's voice was barely a whisper. "Die Luft tötet. Die Luft tötet." The air kills. The air kills. 15 kilometers away at the American artillery position, Technical Sergeant Robert Chen watched his gun crew reload with mechanical efficiency. The new shells looked identical to standard ammunition. Same size, same weight, except for the slightly modified nose cone. Nobody had told them exactly what made these rounds special. Just that they were classified, most secret, and that every single dud had to be recovered and destroyed. Chen didn't need an explanation. The results spoke for themselves. Where conventional fire missions required sustained barrages and follow-up strikes, these new shells were achieving casualty rates that seemed impossible. Forward observers were reporting enemy formations simply ceasing to exist. Chen's gun chief, a veteran of North Africa and Sicily, had pulled him aside that morning. "Whatever's in these shells," he'd said quietly, "it's something the Krauts have never seen before. And pray to God they never figure out how to copy it." Chen loaded another round and pulled the lanyard. 30 seconds later, somewhere in the Ardennes forest, the air exploded again. October 1939. Air Defense Research and Development Establishment, Exeter, England. William Butement stared at the equation that was killing his country. 8,500 shells per aircraft destroyed. That was the mathematical reality of the Great War's anti-aircraft combat. 2 decades later, with bombers flying twice as fast and 3 times higher, British gunners were firing over 20,000 rounds for every German plane they managed to bring down. At that rate, Britain would run out of ammunition before the Luftwaffe ran out of aircraft. Butement drew a simple diagram on his blackboard: a shell, a plane, and between them, radio waves. What if the shell could sense its target? What if it didn't need a direct hit, but could detect when it had flown close enough and detonate itself? His colleague Edward Shire looked at the sketch and laughed bitterly. "Brilliant idea, William. Completely impossible, but brilliant." The problem was obvious to any engineer. You'd need to cram a radio transmitter, receiver, amplifier, and detonator into a space smaller than a thermos bottle, then fire it from a gun at forces that would pulverize any known electronic component. The shell would spin at 30,000 RPM while experiencing temperature swings from Arctic to furnace. No vacuum tube in existence could survive even a fraction of that abuse. But Butement kept calculating. By June 1940, with France fallen and German bombers blackening British skies nightly, he had working prototypes, rocket-launched versions that proved the physics was sound. The electronics functioned. Radar detection worked, but rockets were slow, inaccurate, limited in range. To save Britain, they needed these devices in conventional artillery shells, and that required engineering that didn't exist anywhere in the world. September 19, 1940. National Bureau of Standards, Washington, D.C. Dr. John Cockcroft opened the black leather case and removed a cylindrical object roughly the size of a wine bottle. "This," he said quietly, "is Britain's prototype proximity fuse." Across the table, Dr. Merle Tuve felt his chest tighten. He'd been briefed on the Tizard mission's purpose. Britain was sharing its military secrets with America in case the island fell. But seeing this device in person made the desperation tangible. Cockcroft explained the concept with the clinical precision of a man who'd watched his country being bombed for 40 consecutive nights. The fuse worked in rockets. It could theoretically work in shells. But British industry couldn't solve the fundamental problem. "When you fire a 5-inch naval shell," Cockcroft said, "the electronics experience acceleration of 20,000 times Earth's gravity. For reference, that's enough force to turn a steel bearing into powder." Tuve picked up the prototype. It felt impossibly delicate for a weapon. "Every vacuum tube we've tested shatters instantly," Cockcroft continued. "The filaments tear loose. The glass envelopes implode. We've tried everything: reinforced construction, shock mounting, different materials. Nothing survives." He met Tuve's eyes. "We need American manufacturing capability. Your electronics industry, your resources. We're giving you everything we know because, frankly, we're out of time and options." Tuve set the device down carefully, his mind already racing through the engineering challenges. Miniature radar, rugged vacuum tubes, mass production, all while maintaining absolute secrecy. If Germany discovered what the Allies were attempting, they'd prioritize their own version. "How long do we have?" Tuve asked. Cockcroft's expression was grim. "London is burning tonight as we speak. How long do you think?" December 1940. Carnegie Institution, Washington, D.C. Merle Tuve stood before his assembled team, physicists pulled from universities, laboratories, and research institutions across America. Behind him, a blackboard covered in equations and technical sketches. "Gentlemen," he began, "we have been tasked with building something that every expert says is impossible. A radar system small enough to fit inside an artillery shell. robust enough to survive forces that would destroy a locomotive, reliable enough to work every single time, because in combat there are no second chances. He paused, letting the magnitude sink in. The British have given us the concept, but they've also given us the responsibility. If we fail, their air defenses fail. If their air defenses fail, Britain falls. If Britain falls, he didn't need to finish. James Van Allen, the youngest physicist in the room, raised his hand. Where do we start? Tuve smiled grimly. We start by reinventing the vacuum tube. January 1941. Applied Physics Laboratory, Silver Spring, Maryland. James Van Allen stared at the shattered remains of his 53rd vacuum tube prototype. Glass fragments glittered across the test chamber floor like malicious confetti. The centrifuge had been set to simulate 20,000 Gs, the force of an artillery shell leaving the gun barrel. The tube had lasted exactly 0.03 seconds before its filament tore free and the glass envelope collapsed inward. 53 failures, each one the same. The problem, Van Allen muttered to himself, is that we're building them like we're trying to keep them alive. What if we build them to die, and then resurrect them? His colleagues thought he'd lost his mind, but Van Allen kept sketching. Traditional vacuum tubes hung their filaments from delicate support wires, elegant but fragile. What if instead you locked the filament completely rigid during firing, then released it once the shell was in flight? He called it the mousetrap spring mechanism, a tiny mechanical lock that would grip the filament during the violence of launch, then snap open when acceleration dropped to survivable levels. By March, he had a working prototype. By April, it had survived 50 consecutive test firings. Van Allen walked into Tuve's office and placed the intact tube on his desk without saying a word. Tuve picked it up, examined it, then looked up with something approaching reverence. How many more can you make? June 1941. Naval Proving Ground, Dahlgren, Virginia. The first complete proximity fuse sat in its shell casing like a mechanical brain, a dense cluster of miniature circuits, diminutive capacitors, and Van Allen's revolutionary vacuum tubes, all packed into a space barely larger than a soup can. The assembly contained a miniature radio transmitter broadcasting at 180-220 MHz, a receiver sensitive enough to detect reflections from a wooden aircraft 70 feet away, an amplifier circuit to process the returned signal, a discriminator to ignore false echoes, a detonator triggered by Doppler shift analysis. Tuve's team had crammed an entire radar station into a device that weighed less than 2 pounds. Now came the moment of truth. The test gun, a 5-inch naval cannon, was aimed at a remotely piloted target drone cruising at 200 feet altitude. A conventional shell would need to pass within 10 feet of the drone to have any chance of damage. The proximity fuse theoretically would detonate automatically at the optimal range. Theoretically. "Fire!" ordered the test director. The gun roared. The shell climbed. Observers tracked it through binoculars, waiting for... The explosion occurred exactly 70 feet from the drone. A perfect airburst that shredded the target's tail section and sent it spiraling into the Potomac River. For 3 full seconds, nobody spoke. Then the observation deck erupted in shouts. Men were embracing, slapping backs, some openly weeping. Lloyd Berkner grabbed Van Allen and lifted him off the ground. Tuve stood silent, watching smoke dissipate over the water. He was thinking about the equation that had started this: 8,500 shells per aircraft. With the proximity fuse, that number would drop to a few hundred, maybe less. He was thinking about London's children sleeping in subway tunnels while bombers circled overhead. He was thinking about American sailors who would now have a fighting chance against dive bombers and kamikazes. But mostly, he was thinking, we did it. We built something impossible. August 1941. Department of Terrestrial Magnetism. The champagne had barely dried when reality set in. They had a working prototype. One single fuse. To change the course of the war, they needed millions. They needed production lines that didn't exist. Manufacturing techniques never attempted. Quality control for electronics more complex than anything mass-produced in human history. And they needed it all done in absolute secrecy. Tuve looked at his team. "Gentlemen, we've solved the science. Now we have to solve something harder." He gestured to a map of the United States, marked with dozens of red pins indicating potential factory sites. "We have to teach an entire nation how to build a miracle, without telling them what they're building." January 5, 1943, off Guadalcanal, Solomon Islands. Gunners, mate second class. Marcus Webb had been tracking Japanese aircraft for 18 months. He knew the rhythm of naval anti-aircraft combat like a pianist knows scales, the frantic targeting calculations, the wall of flak thrown into the sky, the sickening probability that most of your shells would explode uselessly in empty air. On good days, you might hit one plane out of 20. Today, his gun captain had assembled the crew of USS Helena's forward 5-inch mount with unusual solemnity. "New ammunition," he'd said, gesturing to shells marked with 3 red bands and stenciled warnings. "Confidential. Destroy if capture imminent. You will not discuss these rounds. You will not speculate about them. You will recover every dud. Understood?" Now, as air raid sirens wailed across the task force, Webb loaded one of the mysterious shells and waited. 15 Japanese dive bombers emerged from cloud cover at 8,000 feet, Val bombers beginning their attack runs. Standard doctrine. Blanket the sky with timed fuse shells set to explode at estimated altitude. Hope the bombers flew into your wall of shrapnel. Webb's gun captain gave a different order. "Target lead aircraft. Fire for effect." The 5-inch gun roared. Webb watched the shell climb, expecting the familiar distant burst. The lead bomber disintegrated. Not clipped, not damaged. Disintegrated, as if it had flown into an invisible wall. The explosion occurred precisely alongside the aircraft's fuselage, shredding it with such violence that the plane seemed to evaporate into a cloud of debris. Webb's jaw dropped. "Load! Load!" the gun captain was shouting. Second round. Another bomber annihilated mid-flight. Third round. A Val attempting to dive was caught perfectly, the shell detonating at the exact moment of maximum vulnerability. Around them, other ships equipped with the new ammunition were achieving the same impossible results. The sky filled with perfectly timed airbursts, each one eliminating a target with surgical precision. The Japanese formation broke apart in confusion. Pilots who had faced American anti-aircraft fire for 2 years were suddenly confronting something that defied their experience. Shells that didn't need to be aimed perfectly. Shells that found you. In 4 minutes, 11 of the 15 bombers had been destroyed. The remaining 4 fled at full throttle, jettisoning their bombs into empty ocean. When the guns fell silent, Webb stood motionless at his station, staring at his hands as if they belonged to someone else. His gun captain was gripping the railing, knuckles white. "In 2 years," the captain said quietly, "I've watched us fire 10,000 rounds and get maybe 30 kills. We just got 11 in 4 minutes." Below decks, the weapons officer was already drafting an after-action report that would be classified secret until 1947. New VT ammunition exceeded all expectations. Effectiveness increase estimated at 700% over conventional AA fire. Crew morale significantly improved by visible results. Request immediate priority resupply of VT rounds for all main battery. January 6, 1943. USS Helena Wardroom. The ship's gunnery officers gathered around a table littered with damage assessment reports. The numbers seemed like fiction. Conventional AA fire success rate, 4 to 6%. E-fused ammunition success rate, 47%. Commander Harrison set down his coffee cup carefully. Gentlemen, I've been in the Navy for 23 years. I've seen technological improvements, better rangefinders, improved fire control, radar targeting. Those innovations gave us incremental advantages. He gestured to the reports. This isn't incremental. This is fundamental. This changes the entire mathematics of naval warfare. A destroyer with VT rounds can achieve what an entire task force couldn't do 6 months ago. Lieutenant Morrison, the junior weapons officer, spoke the thought everyone was having. If we can do this to aircraft, what happens when we use these in surface bombardment? Or against land targets? The room went silent. Harrison smiled slowly. I suspect we're about to find out. January 15, 1943, Pacific Fleet Headquarters, Pearl Harbor. Admiral William Halsey read the Helena combat reports 3 times, checking the numbers for errors. There were none. He picked up his secure telephone. Get me Vannevar Bush in Washington. Tell him I need every VT shell he can manufacture. Tell him I need them yesterday. He paused, looking at the casualty projections for the upcoming Marianas campaign. And tell him he may have just saved 10,000 American lives. March 1943, Crossley Corporations, Cincinnati, Ohio. Helen Kowalski had assembled radios before the war, civilian entertainment consoles for middle-class living rooms. Now she stood at a converted assembly line, piecing together components she didn't understand, for a device whose purpose remained classified. The foreman had been explicit during orientation. You will not discuss your work outside this facility. You will not speculate about what you're building. You will not tell your families, your neighbors, or your priest. Violation means federal prosecution. Helen signed the security oath without hesitation. Her brother was in the Pacific. If this mysterious work helped bring him home, she'd keep whatever secrets they demanded. Around her, 2,400 workers performed the same, precise, repetitive tasks. Soldering miniature circuits, testing vacuum tubes smaller than her thumb, assembling components with tolerances measured in thousandths of an inch. The factory operated 24 hours a day in 3 shifts. The pace was relentless. By mid-1943, Crossley alone was producing 8,000 proximity fuses daily. And Crossley was just one factory. Across America, 87 companies had been converted to proximity fuse production, under contracts that revealed nothing about the final product. Wurlitzer, famous for jukeboxes, now manufactured miniature capacitors. Sylvania, light bulb maker, produced Van Allen's revolutionary vacuum tubes. Raytheon, hearing aid specialists, crafted the amplifier circuits. Eastman Kodak supplied specialized photographic techniques for quality control. General Motors contributed precision machining capabilities. The entire American electronics industry had been mobilized for a single weapon system. 110 factories, 80,000 workers, all operating under absolute secrecy. Engineers from Johns Hopkins Applied Physics Laboratory traveled between plants as anonymous consultants, ensuring quality without ever explaining what the devices would do. Workers knew only their individual task: solder this joint, test this tube, inspect this component. No one except a handful of scientists understood the complete picture. By 1944, American factories were producing 70,000 proximity fuses every single day, more than 2 million fuses per month. An industrial achievement that made the Manhattan Project look small by comparison. September 1944. Lorain, Ohio. Brush Beryllium Company. Margaret Chen wiped the fine metallic dust from her workstation, the same dust that hung in the air of the factory floor, glittering under the harsh industrial lights like microscopic stars. The foreman said it was harmless. just a special metal alloy needed for electrical contacts in the fuses. Wear your mask when you remember. Wash your hands before lunch. No need for concern. Margaret didn't mind. The pay was good. The work felt important, even if she didn't know exactly what they were building. What Margaret didn't know, what none of the workers knew, was that beryllium dust was lethally toxic. Inhaling even trace amounts caused berylliosis, chronic lung inflammation, progressive scarring, respiratory failure. The disease took years to manifest. The government knew, the contractors knew, the workers were never told. By 1945, over 800 workers at beryllium processing plants had been exposed. Many would die slow, agonizing deaths in the 1950s and 60s. Long after the war ended, long after proximity fuses became declassified, long after America had moved on to new weapons and new secrets. Their sacrifice would never be memorialized. Their illness would never be officially acknowledged. They were casualties of a secret war fought on factory floors instead of battlefields. December 1944, War Production Board, Washington, D.C. The statistics officer presented his report to Vannevar Bush with visible pride. Total proximity fuses manufactured, 22,000. Production cost per unit, $18, down from $732 in 1942. Failure rate, less than 2%. Security breaches. Zero. Bush nodded slowly, studying the numbers. 22 million thinking weapons. Mass-produced at a rate Hitler's entire industrial base couldn't match. Delivered to every combat theater. Maintained under perfect secrecy, despite involving nearly 100,000 people. "Have you calculated the lives saved?" Bush asked. The officer consulted his notes. Conservative estimate, 135,000 Allied casualties prevented. Possibly double that if you include indirect effects. Shorter battles, reduced exposure to enemy fire, psychological impact on enemy forces. Bush set down the report. And the workers exposed to beryllium? A pause. Estimated at 800 to 200 individuals. The medical division suggests we defer investigation until after the war. Bush's expression hardened. He thought of Helen Kowalski and Margaret Chen and thousands like them, patriots who built miracles while breathing poison, who won a war while losing their health. "Make a note," he said quietly. "When this is declassified, we owe them the truth." The note was made. The truth would take 40 years to emerge. Guadalcanal, January 1943, the first proximity-fused shells, fired in anger, turned the night sky into a slaughterhouse. Japanese bombers approaching at 12,000 feet encountered a new mathematics of death, airbursts that found them with supernatural precision. 11 aircraft destroyed in 4 minutes. The survivors fled in panic, radioing warnings about American shells that tracked targets. The weapon had announced itself. Solomon Islands, March 1943. Navy gunners discovered an emergent phenomenon the scientists hadn't predicted: linked detonations. When multiple proximity-fused shells were fired simultaneously, their radar signals could trigger sympathetic explosions, creating overlapping kill zones that turned cubic kilometers of airspace lethal. Japanese formations approaching the task force at Kula Gulf flew into what appeared to be solid walls of shrapnel. 27 aircraft disintegrated in 8 minutes. American ships reported expenditure of just 186 rounds. The old ratio, 2,500 shells per kill, was now a historical curiosity. Mariana's Turkey Shoot, June 19, 1944. The Imperial Japanese Navy launched its final desperate carrier offensive. 373 aircraft against the American Fifth Fleet. What followed wasn't a battle. It was an extermination. American ships equipped with proximity-fused ammunition created an aerial killing field 50 miles wide. Japanese pilots, Many barely trained, flying obsolete aircraft encountered defensive fire of impossible accuracy. Planes exploded before reaching bombing range. Formations dissolved under precision airbursts. By sunset, 315 Japanese aircraft destroyed. American losses, 29. Pilots returning to their carriers reported the same observation. The sky itself was fighting against us. The Imperial Navy's carrier aviation capability had been erased in a single afternoon. Okinawa, April 1945. The kamikaze war brought a new horror: suicide pilots who couldn't be deterred by fear. But they could be killed. Proximity fuses transformed picket destroyers into mechanical executioners. Ships stationed on radar picket duty, previously the most dangerous assignment in the Pacific, now achieved kill rates approaching 60%. Kamikazes disintegrated in mid-dive, torn apart by shells that detonated at precisely calculated moments. USS Laffey, defending against 22 kamikaze attacks in 80 minutes, survived only because of proximity-fused ammunition. 16 attackers were destroyed before reaching the ship. The weapon designed to save London was now saving American sailors from diving fire. London, June 1944. Hitler's V-1 buzz bombs were supposed to break British morale. Pilotless cruise missiles carrying 1,300 pounds of explosives. In the first week, they terrorized the capital. Then British anti-aircraft batteries received American proximity fuses. Interception rates skyrocketed from 24% to 79% in 3 weeks. V-1s approaching London encountered walls of perfectly timed airbursts. The weapons that were meant to be unstoppable became target practice. Churchill would later write, "The proximity fuse saved London more certainly than the fighters of 1940. Antwerp, October 1944. Germany launched 8,000 V-1s at the critical Belgian port. American-supplied proximity fuses achieved 91% interception rates, the highest of the war. The harbor that sustained Allied logistics remained operational. The invasion of Germany continued uninterrupted. Hitler's terror weapons had become statistical footnotes. Ardennes Forest, December 22, 1944. The Battle of the Bulge marked proximity fuses' ground combat debut and their most devastating performance. German infantry advancing through the forest encountered artillery that didn't need to see them. Shells burst overhead with metronomic precision, turning every attack into suicide. Battalions dissolved under airbursts that made cover meaningless. One American artillery battalion reported expending 500 proximity-fused shells and achieving estimated 70% casualty rates against dug-in German positions, 10 times conventional effectiveness. Oberst Wenzel's diary entry, "We cannot advance, we cannot defend, we cannot hide. The American shells find us everywhere." Within 2 weeks, German offensive momentum had collapsed. Not from lack of courage, from unsustainable casualties inflicted by a weapon that erased every tactical advantage they possessed. April 1945, across every front. From the Rhine to Okinawa, proximity fuses had become standard ammunition. 22 million units deployed. Present in every naval engagement, every amphibious assault, every artillery barrage. The weapon that seemed impossible in 1940 was now ordinary, expected, essential. Allied commanders no longer planned operations wondering if they could achieve air superiority or suppress enemy positions. They simply assumed it. The mathematics of war had been permanently rewritten. March 1945, Kummersdorf Proving Ground, outside Berlin. Dr. Herbert Wagner stared at the dissected American artillery shell on his laboratory table as if it were an artifact from another civilization. Wagner was one of Germany's leading electronics experts, designer of guided bombs, pioneer in radio control systems. He had been summoned to examine a proximity fuse recovered intact from a dud round near Aachen. For 3 hours, he had meticulously disassembled the device. Now he sat in silence, his hands trembling slightly. "Well?" demanded the Wehrmacht liaison officer. "Can we copy it?" Wagner looked up, his expression hollow. "Copy it? We cannot even comprehend it." He gestured to the components spread before him. Miniaturized vacuum tubes no larger than a bullet, circuits packed with impossible density, a radar transmitter smaller than his thumb. This represents manufacturing precision we cannot achieve, miniaturization techniques we have not developed. Most critically, he held up one of Van Allen's reinforced tubes, vacuum tubes that survive 20,000 times normal gravity. Our best military tubes fail at 200 Gs. The officer's face darkened. "So we do nothing?" Wagner set down the tube with exaggerated care, as if it might shatter. "We do nothing because we can do nothing. The Americans have created electronics that belong in science fiction. This device has computing capability equivalent to a room full of our equipment, compressed into a shell casing. The man-hours required to manufacture one of these," he trailed off, calculating mentally. Germany's entire electronics industry could perhaps produce 50 units per month. The Americans are clearly manufacturing millions. He stood, walking to the window overlooking the proving ground. "We spent 5 years perfecting tanks, aircraft, submarines, mechanical superiority. The Americans spent 3 years making their ammunition intelligent. They have beaten us not with better soldiers, but with better science." The officer left without another word. Wagner remained at the window, watching snow fall over the Reich's crumbling infrastructure, thinking about the terrible arithmetic of industrial warfare. Germany had fielded the world's finest soldiers, the most disciplined army, the most experienced combat commanders. None of it mattered against an enemy whose shells could think. April 1945. Imperial Japanese Navy Archives, Tokyo. Lieutenant Commander Mitsuo Fuchida, survivor of Midway, veteran of dozens of air battles, read the compiled pilot reports with mounting dread. American anti-aircraft fire has become supernatural. Shells explode with impossible accuracy. 3 of our formation destroyed by airbursts that appeared to track our movements. The sky has eyes. There is no evasion. I watched Tanaka-san's plane disintegrate. The shell exploded exactly alongside his cockpit, as if it knew he was there. Fuchida set down the reports. He had flown against American carrier groups in 1942, when Japanese pilots dominated the Pacific skies. Then, American anti-aircraft fire had been heavy but inaccurate, something you could navigate through with skill and courage. Now, skill was irrelevant. Courage was suicide. The Americans had achieved what no military in history had accomplished. They had made the air itself lethal. Japanese pilots weren't being outfought. They were being outscienced, killed by mathematics, murdered by physics, erased by engineering they couldn't comprehend. Fuchida opened his diary and wrote what he knew would be his final strategic assessment. "We trained warriors. They trained weapons. We cannot compete with an enemy whose ammunition is smarter than our pilots." May 1945. Interrogation Facility, Luxembourg. The captured German artillery officer refused to meet his interrogator's eyes. "Your defensive positions," the American intelligence officer prompted. "Why abandon them without a fight?" The German's voice was barely audible. "Because there is no defense. Your shells. They find us. In trenches, behind walls, under trees. It makes no difference. We trained for 30 years to use terrain, to dig proper fortifications, to maximize cover." He finally looked up, his expression haunted. "Your weapons made all of that obsolete. You did not defeat our tactics. You rendered tactics themselves meaningless." The interrogator waited. When a German soldier takes cover from artillery, the officer continued, he thinks, I am safe. When your new shells arrive, he learns, there is no safe. The weapon knows where he is. He fell silent for a long moment. You broke something more important than our lines. You broke our doctrine, our training, our understanding of warfare itself. The interrogator closed his notebook. The war was over. Germany had lost to science. August 1945, Carnegie Institution, Washington, D.C. Merle, Tuve stood in his now quiet laboratory, holding one of the devices that had consumed 5 years of his life. The war had ended. Japan had surrendered. The proximity fuse, still officially classified, had fired its last combat round. 22 million units produced. Over 135,000 Allied lives saved by conservative estimate. Entire enemy formations erased. The mathematical balance of warfare permanently altered. But Tuve wasn't thinking about victory statistics. He was thinking about what they had created. Not just a weapon, a precedent. The proximity fuse was humanity's first autonomous killing machine, a device that sensed, decided, and acted without human intervention. It chose the moment of its own detonation. It selected its optimal killing radius. It made life and death calculations at electronic speed. They had taught metal to think, and now that knowledge couldn't be unlearned. 1946, the 1950 White Sands Proving Ground, New Mexico. The German V-2 rockets captured at war's end became test beds for American engineers studying a new question. What if the proximity fuse's technology wasn't the endpoint, but the beginning? What if you could make the entire weapon intelligent, not just its detonator? Teams led by former proximity fuse engineers began embedding guidance systems into missiles. The principles were identical: miniaturized electronics, radar sensing, autonomous decision-making. But now the device didn't just choose when to explode, it chose where to fly. The Nike Ajax surface-to-air missile, deployed in 1953, traced its lineage directly to Van Allen's vacuum tubes and Berkner's circuit designs. It was a proximity fuse that could steer itself, a thinking weapon with wings. The age of guided missiles had begun. 1947, Bell Telephone Laboratories, Murray Hill, New Jersey. 3 physicists, Bardeen, Brattain, and Shockley, demonstrated the first working transistor, a solid-state electronic component that could amplify signals without vacuum tubes. Their innovation would eventually revolutionize computing, telecommunications, and electronics worldwide. The transistor would become the foundation of the digital age. But the research that made it possible had been funded by wartime electronics programs. The manufacturing techniques had been perfected in proximity fuse production lines. The miniaturization imperative, the need to compress complex circuits into impossible spaces, had been driven by artillery shells spinning at 30,000 RPM. The transistor's inventors never worked on proximity fuses directly, but they built their breakthrough on infrastructure created to make shells think. 1958. Formation of DARPA. The Defense Advanced Research Projects Agency was established with a mandate: ensure America maintained technological superiority in weapons systems. Its first priority: autonomous guidance systems, smart munitions, precision strike capability. Every program traced its conceptual ancestry to the same source: the proof, established in 1943, that weapons could be made intelligent. The proximity fuse had demonstrated that the side with superior science could neutralize the side with superior soldiers. That lesson would define Cold War strategy for 4 decades. 1991, Persian Gulf War. An Iraqi Scud missile climbed toward Allied positions in Saudi Arabia. A Patriot interceptor missile launched automatically, its radar-guided warhead tracking the target with precision impossible in World War II, but using principles perfected 50 years earlier. The Scud disintegrated in a proximity-fused airburst. Reporters described it as cutting-edge technology. Engineers recognized it as genealogy, a direct descendant of the device Merle Tuve's team had built in 1941. 2T25. Present day. Every precision-guided bomb, every anti-aircraft system, every autonomous drone, every smart missile deployed by every military on Earth, they are all children of the proximity fuse. The technology has evolved beyond recognition. Modern weapons use GPS, laser guidance, artificial intelligence, computational power millions of times greater than Van Allen's vacuum tubes. But the conceptual breakthrough remains unchanged. Weapons that sense their environment. Weapons that process information. Weapons that make decisions. The proximity fuse didn't just win World War II, it created the template for every conflict that followed. Wars where victory belongs not to the bravest army, but to the smartest arsenal. Merle Tuve died in 1982, his wartime work still largely unknown outside classified circles. But his legacy surrounds us, invisible, ubiquitous, permanent. We live in the world the proximity fuse made. A world where weapons think. May 8, 1945. American POW camp, Reims, France. Oberst Friedrich Wenzel sat on his bunk in the officers' barracks, a borrowed pencil in his hand, writing what he knew would be his final wartime entry. 4 months had passed since that December morning in the Ardennes, the morning the sky had learned to kill. In those 4 months, he had watched the Wehrmacht collapse, not from lack of courage or tactical skill, but from something more fundamental: obsolescence. German soldiers had fought with the same discipline and determination that had conquered Poland, France, and nearly defeated Russia. It hadn't mattered. The Americans had changed the rules. Wenzel thought about the thousands of men he'd watched die, not in glorious charges or heroic last stands, but in systematic annihilation by weapons that seemed to possess awareness. Artillery shells that exploded with impossible precision. Anti-aircraft fire that turned the sky into a graveyard. Defensive barrages that made terrain itself irrelevant. His military education, decades of study in tactics, doctrine, combined arms warfare, had been rendered meaningless by engineers in laboratories he'd never heard of, solving problems he'd never imagined existed. He began to write. May 8, 1945, the war is over. Germany has surrendered unconditionally. I have had 4 months to contemplate our defeat, and I have reached a conclusion that would have seemed impossible to me in 1939. We were not defeated by better soldiers. The American infantry we faced were often inexperienced, sometimes poorly led. We were not defeated by superior tactics. Our operational doctrine remained sound until the end. We were not defeated by greater courage. No soldier fights harder than a German defending his homeland. We were defeated by science. The Americans conceived a weapon that should not have been possible with 1940s technology, a device that transformed every artillery shell into an intelligent killer. They solved engineering problems our best minds declared unsolvable. They manufactured 22 million units with precision we could never match. They deployed this weapon across every theater while maintaining perfect secrecy. Most remarkably, they accomplished this not through authoritarian efficiency, but through democratic cooperation. 87 companies, thousands of scientists, 80,000 workers, all contributing pieces of a puzzle whose complete picture remained hidden. This, perhaps, is the true lesson of the war. We believed in the supremacy of will, discipline, martial tradition. The Americans believed in the supremacy of engineering, mass production, and scientific collaboration. They were correct. History will remember the great battles: Stalingrad, Normandy, Midway. But historians should remember this. Wars in the modern age are not won on battlefields. They are won in laboratories and factories. They are won by nations that can mobilize not just armies, but entire industrial civilizations towards scientific innovation. I think of that December morning when the sky first exploded above us. My men thought they were experiencing some new form of artillery tactic. They did not understand, could not understand, that they were witnessing the future of warfare. A future where weapons possess intelligence, where ammunition makes decisions, where the advantage belongs not to the warrior but to the scientist. The proximity fuse was small enough to hold in one's hand. It weighed less than a kilogram, yet it changed the outcome of the war more certainly than any panzer division or battleship. Germany fielded the world's finest soldiers. America fielded the world's smartest weapons. In the end, that was the only equation that mattered. Wenzel closed his diary and set down the pencil. Through the barracks window he could see American soldiers, young men, laughing, playing baseball in the spring sunshine. They looked nothing like the hardened warriors of German propaganda. They looked like farmers and shopkeepers in uniform. But behind them stood something Germany could never match, a nation that had transformed its entire industrial capacity into a weapon, a democracy that had mobilized science itself for war. Wenzel lay back on his bunk and stared at the ceiling. Somewhere in America, in laboratories he would never see, engineers were already designing the next impossible weapon. The future belonged to them. It always had.